This is surprising though. I still have like
Okay.
a pretty solid.
We shouldn't have it away from
Because you
Valve.
can't pass it, you shouldn't get some.
Okay.
And then this is when he started printing.
That's the number one.
So I never wrote with this again.
Yeah.
Okay,
I'm getting a 33%.
so let's talk about 51 and 52. So here was the problem that classical physics had with the idea of the modern understanding of the atom, is that they just hated it. Because it didn't make any sense, okay? No, they did. They despised it. It's just like, this is just stupid.
Oh.
Because they were, in natural human endeavors, they were trying to overlay a macroscopic view onto the atom. And they thought, well, if it works on the big scale, it should work on the small scale. So, if you look at John Dalton's atomic theory, that was the first one that really had any kind of prominence in scientific circles. And Dalton was a history, or had studied the history of this. And the atom came from the Greeks atomus, who thought particles were indivisible. So the thought process on that, if you want a visual, was that here I have a piece of aluminum. Okay, I take this piece of aluminum and I tear it in half. Okay, it's still aluminum. I tear that in half. It's still aluminum. I keep tearing and I keep tearing and I keep tearing. So it tears on the gaps in between the particles. Okay, that's what allows you to separate them. So at some point, and they envisioned like this infinitely sharp knife, and you keep cutting this, and you keep cutting this, and you keep cutting this. At some point, you're going to reach a point where you can't cut it anymore, okay? And once you reach that point where you have that solid, indivisible particle, that's what they viewed as the atom. And so they viewed it as basically, in modern terms, these really tiny Lego blocks. And if you arrange these Lego blocks in one way, you get Oreo cookies. If you put them another way, you get squirrels. And it's true. And some of them are capable of producing fire, and some of them are liquids, and some of them are gases. But at the end of the day, they said if you divide it at some point, you can no longer divide that point, and that's where the Greek word atom comes from, the word indivisible. Not invisible, but indivisible. And that was cool. And then here was the first problem, was that J.J. Thomson discovered the electron. Actually, he discovered the mass to charge ratio of the electron. And he used a cathode ray tube, and these particles were flowing across, and they didn't know what they were. And he figured out that they could interact with an electric field. Oh, okay, great. Well, then that's how I figured out they were negatively charged. And then based upon how much they deflected, he was able to find that charge to mass ratio. And then said, okay, well, great, now we have electrons. Well, there has to be protons, or we wouldn't be here having this discussion. Because if you look at the universe, it's a good thing there was this balance. And we're going to talk a lot about neutrons today. We haven't really talked about neutrons. Mainly because neutrons are important, but they just don't have any charge, so they just kind of sit there and go, so, okay? But they allow the nucleus to be stable. So Rutherford does his work, which was in contrast to the plum pudding model. Of course, that was all done by the British. This was all in England at the time, because that's where all the quantum physicists were working. And the initial model was what they called the plum pudding model. And so basically, once they discovered that there were electrons, they said, okay, here's our atom, which is this Lego. And they said, well, the negative and positive charges are evenly distributed, okay? And that fit because, again, they were forced to explain the stability of atoms. How are atoms stable? And so they said, okay, well, if there was negatively charged particles, they figured there had to be positively charged particles. So this was like the yin and the yang, okay? It balanced the repulsion between the like charges with the attraction of the unlike charges, okay? And so there was repulsion, there was attraction, everything was stable, atoms were stable, life was good. Well, here's the problem. Rutherford comes along, who we talked about yesterday, throws the tennis ball blindly at the golf or the bowling ball in the back of the room. Mostly goes through, every once in a while it hits and bounces back. Rut-row, this is problematic. And so this is what's happening on 51, is you're saying, okay, if the nucleus is as small as it is, and this introduces this distance of femtometers, okay? And so if you're not sure, you probably have never worked with femtometers before, okay? Prefix is like 10 to the negative 15. So what you can do then is find the force that exists between these two protons, which is like 60 newtons, okay? So your answer to 51A is about 60 newtons. So here's what I want you to think through. Is that so inside the nucleus of every atom inside your body, there's a force of 60 newtons trying to pry those protons away from each other. So if you consider, here's 1 kilogram, weighs about 10 newtons, 9.8, let's call it 10, okay? So 60 newtons would be about the weight of 6 kilograms. So there is a weight of 6 kilograms trying to push apart every proton in every nucleus, in every particle inside of your body. Well, it's just like rut-row. Well, what do we do now? Obviously, they're stable. And so on B, they said, well, maybe it's gravity. Well, if you do the gravitational calculation on B, using the old school F equals big G M1 M2 over D squared, you get like 10 to the negative 35th. So gravity isn't going to do jack to try and hold these things together because, yes, it's really, really close, but they're also really, really small. So gravity can't do it. And so then that led to the idea of this, it is not the most clever term in the world, but it works. And they said, okay, well, there has to be a stronger force than the electrostatic force is. Because the electrostatic force, if the universe only had gravity and the electrostatic force, we would not be here having this discussion because of the fact that you could never hold a nucleus together because it would go flying apart. So they said, okay, well, we have to have a stronger force than the repulsive force. And they were clever, and they said, oh, let's call it the strong nuclear force. Cool, okay? So the strong nuclear force is stronger than the electromagnetic force. But it acts over the shortest distance. So it isn't like, hey, here's 2 protons walking down the street. Hey, how you doing, buddy? I'm good, okay? And then all of a sudden, boom, they're going to get sucked together by the strong nuclear force. This is why, Sydney, it's so difficult to make helium, okay? Everybody says, hey, we're running short of helium. How difficult can it be to make helium? So you Google how to make helium. Oh, here's your recipe. All you need is 2 protons, 2 neutrons, and 2 electrons. How difficult can it be? Okay? Seriously. Well, it's not that complicated. Let's just take the 2 protons and the 2 neutrons and we'll smash them together, okay? And then they're going to get sticky, right? And then we'll just throw in the electrons and they'll begin to orbit and voila, we have helium, okay? How difficult can that be? Well, extremely difficult. Mainly because of the fact that even if you shoot these protons at each other, which would be incredibly difficult to do because it's just this tiny bit of matter, you have to get them so close for the strong nuclear force to take hold. And that's why it's so incredibly difficult to make helium. So one of the things that, and hopefully they have this online, maybe in the next 3 or 4 years, is that, and we'll go through the math, is that you can take hydrogen and fuse it together and then get helium, which is what's happening in the sun. So a fusion reactor, the beauty of the fusion reactor is that, and we'll go through the math here in just a second, is that the mass of the particles before relative to the helium is slightly more. And in that process, you lose some mass, and that's what is converted into energy by Einstein's equation, E equals mc squared. So here's the problem with the nucleus, is that, like many things in the quantum world, it doesn't make any sense. So the reason that we can't make helium, even though it's a relatively simple recipe, is that we can't get those protons close enough under normal conditions, because it isn't like, oh, I'll put a helium, or I'll put a proton here, and then I'll put a proton in the end of a hammer, and I'll just smash them together. Okay, there, we'll make helium. Bam, bam, bam. No, okay? No. Bad, it's not gonna work. Okay, so there's that. So that 51 is the heart and soul of the problem with the nucleus, is that there's 60 newtons of force trying to push apart every proton that's close together inside every nucleus of every atom inside your body, okay? But thankfully, there's the strong force. Okay, if the strong force didn't exist, we wouldn't be here having this discussion. Now, so on 52, okay? So head-on collision, closest approach, 6.24, alpha particle in the center of the nucleus is 6 femtos. The nucleus is an atom of what element assumed that the nucleus is heavy enough to remain stationary during the collision. So there was a couple of things in retrospect that Rutherford got lucky on. One is that he picked gold. Gold's a relatively massive nucleus, okay? So, and then what he was shooting at them, the alpha particle, which came from the radioactive decay of thorium, and you couldn't see them. Everybody has this model. It's like, oh, you can see them. They're like tiny little marbles. No, it's the nucleus of a helium atom, okay? You can't see them. So the gold foil had a relatively massive nucleus. And so when it would get hit with that, which is the alpha particle, which is relatively small, it's just a helium nucleus, then that gold massive nucleus basically didn't budge, okay? So that's like you're driving your car and you run into like a fly while you're driving, okay? That's about the same equivalence. So is the fly going to alter the momentum of your car? Yes. Enough to measure? No, okay? So that's why he got lucky that it was such a massive particle, and that's why it would hit and it would bounce back. So here's the basic idea, is that, so here's this alpha particle, and this is one of the things, certain terminologies you need to know before the test on Monday. One is an alpha particle. All it is a helium nucleus without the electrons, okay? That's it. That's an alpha particle. And that Rutherford didn't even know what he was shooting at the time. That's what we called an alpha particle. So, if you look at what's going to happen, so you have the 6.24 MeVs. So, when this comes in, it's kind of like this cart rolling towards the wall. So here's the alpha particle. The wall is like the gold nucleus. It's going to come in here and it's going to hit, and it's going, at some point it's going to stop. So that point of closest approach would be how far does the spring compress? Okay, because once it's compressed, how much velocity does it have? Zero. Okay, it has none because of the fact that you've stored all that energy. So what it's saying that is the 6.24 mega electron volt alpha particle, that's how much energy is bringing into this. So if you look at how you calculate UE, which is KQ1 Q2 over distance squared. So the 6.24, that's the amount of energy that you bring into it. So that's your UE value. That's how much energy that you have to start with. So you're going to know that value. Then you're also going to know the fact that, but this is in, and this is what you have to decide. these are in MEVs, okay? If you're gonna roll with K, what are the units for K? Newtons squared over kilograms squared, or coulomb squared. Coulomb squared. So you can't work in MEVs and newtons and meters squared. You need to roll those MEVs into joules. So then you're gonna know the value of your energy. You're gonna know the distance. Now, because it's an alpha particle, what's the charge of, like, on the alpha particle? What's the total charge?
2 plus.
Two, just two?
2 plus.
But in terms of your Q value, what are you gonna use?
2Q.
2Q, so you gotta take 2 times 1.60 times 10 to the negative 19th coulombs to get that Q value. So then you can find the second Q value, because then you're gonna know the distance, you're gonna know the UI, you know the K, you're gonna know the Q, work backwards, and you should come up with a low density metal as the identity of the unknown metal. Cool with that? So 52 isn't that horrible, it's just more of a conversion problem than about anything. So, make sure, like on 4 and 5, do not randomly just write down numbers and think I'm gonna know what the numbers are, okay? So like on 5, you got beryllium, carbon, nitrogen, and then each one of those, you need the number of electrons, the protons, and the neutrons. Make sure I know what they are. I swear to you, if you just write down numbers, I am just going to lose my mind, okay? What's this? So, just make sure you know what they are. On problem number 8, and this is kind of like what we talked about yesterday, you've got those different energy levels. What wavelengths appear on the emission spectrum, and then on part B you have the absorption spectrum. So you, on 8A, your answers should, this is an ish, you should have 3 wavelengths, roughly between 300 and 800. Okay? On part B, you should only have 2 wavelengths. So remember, emission spectrums are more complex, because when you have emission spectrums, like let's say you have these different values. So emission spectrums, you can go from the top all the way down, you can go from here, you can go to here, you can go from here, okay? And so if you're in stats, okay, you can work out the probability of picking one of the transitions, okay, randomly, if you look at the total number of them, okay? So there's your applications of stats. So your answer to 8B should have 2. One of them is around 300 and the other one is around 800. Charles?
Did you just
Like
dab
that?
in 2025? I did. We're bringing it back.
You're bringing
Dab.
it back and failing.
Wow.
Okay.
Cohen leaves and look what happened. Now, let's talk about question number 7. And it says, when n equals 3, state of hydrogen, E3 has a value of -5, why is the energy negative? So there's a couple of different ways you can approach that. One is that if you have a hydrogen atom, okay, it only has 1 electron, and that's most likely going to be in which energy level? Well, n equals 1, the first energy level, closest to the nucleus, right? That's where it's most likely going to be. So you can kind of get a little bit philosophical, because that's the lowest energy level. So if you bump it up to n equals 3 and it makes that transition back down, it has to lose energy to come back down, and that's how much energy you would see like in the form of light. So one way you can view it is if it would have to lose energy to go from n equals 3 back down to its normal state. And that's how much light energy you would see in the photon being given off. The other way you can view it, and I always hated this, and I still just, it still doesn't make, it's just annoying. I mean, it makes sense mathematically, but that's if you have an electron that's infinitely far away, and you were to take that electron and you could move it to that point. Well, if you have a positively charged nucleus and a negatively charged electron, it wants to go in that direction. So you would have to be pushing against it to get it to that point, okay? So, because the electron wants to go in that direction, and then the negative value is just indicating that you would be pushing against it. Now, but this is where that concept makes a little bit more sense. When you get to question B, it says, what is the physical significance of that specific number? That makes sense when you go to answer B, because if you were to take that electron and make it completely leave the bound state of the hydrogen atom and make it go to infinity, that's how much energy you would have to put into it, okay? So that's the other side of it. Or you can explain it in terms of, hey, that's how much energy it would gain or lose if you were to go through that transition state back to the first one. I don't care, okay? Just, that's more of a philosophical discussion and how you want to interpret what a negative electron volt energy means. I promise you, I am not going to give you negative electron volt energies on the test. Mark my words, okay? Not going to happen. Promise you that, because it's just annoying. It's a good mathematical model, but it physically doesn't make any sense. So, all right. Last time I will ask you this. The proper response would have been, Mr. Burkett, that's a sad day.
What?
I've complex feelings about it, you could say.
You should write a paper.
As Mr. Fry would say.
Conflicted.
Complex.
Let's go with conflicted.
Bittersweet.
He's having a shift.
Bittersweet.
I'm having an emotional shift.
I didn't see you.
Okay.
Oh,
But is it a Doppler shift?
That's fine.
No, it's weird.
All right. Anything else? Going once, going twice, gone to infinity. So,
Yeah, volume has been 50% of what it has been. It has always been 50% of what it has been if it wasn't here, but never 0.
yeah.
Forgot to say get that handed in.
Huh?
You messed it up.
Okay, all right, my bad. I thought that would have been implied at this
I
point.
know that's the most important
Okay,
part.
I'll try it again.
Yeah.
Once, twice, gone to infinity. Get that handed in. Okay.
That's like the key part.
But it's also not realized.
Right down the bottom.
I still have it, my charge. Remember tires, turns to -21.
I don't understand.
That's right.
It's me.
Like I have the idea, I just can't do it right.
I did it.
I couldn't get the answer.
I still have to know what we're learning.
I'm so confused.
I'm almost free.
It's 0.05%.
Hold on there, Chuck. You have 3 1/8 day left.
You said you have to know your words.
Yeah, if you check your work.
Like, I changed it, it's
Yeah, definitely.
okay. No, at the time you thought it was that.
Line
We got blind G stability, guys.
Hey, we're almost done.
Kevin,
If we could
so you know how
use
Loving was trying to announce one of the athletes who's done basketball 4 years in a row, tennis 4 years ago. I thought it was Charles.
I know, I was like, it's Charles.
Yeah,
Charles.
and then they said Alec. I was like,
And then I heard
what?
signed Kansas West, and I was like,
Yeah.
Yeah.
Yeah, you got robbed.
There's no way they're about to.
No,
It's not my game.
And the thing is, I saw your head pop up. I saw.
They're low-key mentioning. Yeah. I
Yeah.
was confused. I was like, it's gonna be
I thought it was
I was
you.
like,
I thought it was
and then when
Charles.
they said, Wesley, I was like,
That's what,
yeah.
yeah.
They like,
Yeah, but then
But yeah, I was sitting almost right behind Charles, so
They
all
don't
I see
like have
is.
to suffer.
Yeah.
this is not
Somehow
about
an
to
airplane
happen. I
falls
do
out
not
of the
agree.
sky on top of him and he lands.
Yeah, you do.
I will say he
I mean, he doesn't even have good enough aim to knock a Chromebook off my head from there to there.
Okay.
Yep.
Scared for my life for about a second.
Can we give Persona a
Okay, so here's the last chapter. And it is kind of cool to think that we have gone through basically about every chapter in this book. I mean, that's a lot of stuff.
That's a lot of pain.
It has been. It's been a good journey.
A lot of pain.
What a grind.
It's been a grind.
Yeah.
It's- some days more than others.
Yeah.
So, but this is what I tell people. I said, you know, I look at what you guys are going to know about physics coming out of high school. I didn't study this stuff in detail until I was like a sophomore in college. I mean, so what, you know, what the knowledge that you guys are able to obtain going into college is so much, you know, more advanced that I didn't have the opportunity to. I mean, yeah, we had a Chem 1 class at Old High School, one chemistry 1 class, and we had a physics class. And the physics class basically, we didn't do a whole lot with that either. We built rockets, you know. That was what I remember. And so, you know, but then what you guys are being exposed to literally is stuff that most people don't study until they get to, in the old days, it's like, oh, you learned that in college. So you guys do have, you know, a tremendous advantage, like, hey, you can go into college and, you know, hey, I already know a lot of this stuff, like I was talking with, Lonnie Hampy. He came and saw me, and he was taking physics up at K-State. And, he said, you know, it's just weird the way the teacher teaches it, it's just wonky. But he said, he goes, there are so many people flunking that class. He goes, I've got high B, low A, and only because I already knew it. And so I didn't have to worry about learning the physics, they just weirdly how they do the math and the assessments. And because the teacher really doesn't explain it. And so he goes, if I didn't already know it, I'd be toast. And so that's the advantage that you all have going into it. It's like, hey, I know the physics, yeah, you might have to retake and figure out the calculus part of it. But it isn't like in calculus-based physics, there's 4 laws of Newtonian mechanics. It's like, oh, calculus, there's actually 4. Okay, we'll talk about, no, okay, momentum is still momentum. Electric fields are still electric fields, it's just how you handle the calculus. Okay, so here's gonna be the last big thing. And one of the things that I had to figure out, and again, this was now tough, how you even figure this out. And that's the relationship between the number of protons and neutrons in the nucleus of an atom. Neutrons were tough to find. You don't have neutrons floating around, and they don't interact with an electric or a magnetic field. So basically what happened is that they were finding nuclei that were bigger than what they should have been based upon the pure number of protons. And what they found is that the increase in mass was always the same. So, and which was basically corresponding to the exact same mass of the protons. So they said, okay, great. So the universe, for whatever reason, has these tiny, tiny, tiny chihuahuas of electrons that are negatively charged. The universe, thankfully, also has these big, massive protons, which conveniently have the exact same charge as the electron does. And then you've got these big, chunky neutrons, which really don't do anything except help stabilize the nucleus. If the universe did not create neutrons, we would not be here having the discussion. Like, you can't even make helium without neutrons, okay? Because you have to have 2 protons and you have to have 2 neutrons. So literally, if the universe did not create neutrons, we would not be here having this discussion. So, once they were able to figure that out and go, okay, great, protons, neutrons, which flew in the face of Dalton's atomic theory, because Dalton's atomic theory said that there shouldn't be isotopes, because he said all nitrogen atoms are identical, but they're different from all oxygen atoms. So Dalton's theory had no concept of isotopes, because they didn't have the capacity to measure that small of difference between the different isotopes. So now, here's a common misconception. This number over here on the y-axis is not the mass number, okay? It is the number of neutrons. It is not the mass number, it's the number of neutrons. So up to about 18, once you get to about chlorine, the number of protons is the same as the number of neutrons, and these exist in 1-to-1 ratios, because here's the classic example. What's the relative atomic mass of carbon? 12, okay?
Carbon 14 is radioactive.
He said it with so he said it with so much confidence. It almost
Yeah,
made me
and it
question
was so
12.
confidently wrong.
It almost made me question 12.
Charles, what's the relative atomic mass of nitrogen?
14.
There you go.
We got that.
There we got, you're just off by an element, okay? So, you look at oxygen, nitrogen, okay, carbon. All of them have the same number of protons as they have the same number of neutrons, and you have this line of stability. But eventually this veers off, okay, and veers up like this. So once you get into the bigger nuclei, you have to have more neutrons than you have protons. So this line of stability doesn't maintain that 1-to-1 slope. It curves up. The reason being is that as that nucleus gets bigger and bigger and bigger, it's kind of like at a party. So again, keep in mind, do the protons want to be near each other? No. Okay? In no way, shape, or form. So basically, it's kind of like you're at a party, and initially there's like 8 people, and they don't like each other, so you're going to have 8 other people there to kind of balance things out, okay? But once you hit about 20 people, it's like, I can't have a 1-to-1 ratio of sane people and people that don't like each other. I got to call in reinforcements, because once you hit 20, there's too many other interactions that can happen. So that's why as you get more and more and more protons in there, eventually you deviate from that 1-to-1 ratio, because it takes more and more and more neutrons to maintain the stability. But here's the downfall. It's kind of like building a tower of Jell-O, okay? If you build that tower of Jell-O so tall, it's there, but it becomes very, very unstable. So it's like you give one good, bump to it, bam, falls apart. And that's what happens with nuclei as well. So this is why when you get to the very bottom of the periodic table, you have those elements, but you can only create them in basically particle accelerators. And they only exist for very brief moments of time. Like we can make them, we can detect them, but then they automatically decay back into their simpler constituents. So the only way you can make them is in an artificial way. It would be like, hey, I want to build a tower of Jell-O 20 feet tall. Cool, okay? You're not going to do it just a freestand of Jell-O. But if you can shore it up and artificially support it, then you can build it. But as soon as you take those artificial supports away, tower comes crashing down. That's what happens with nuclei. Okay, now, so here's one of the most important things, and you've got to reference this table in the back of your book. So if there's, this needs to become your friend. So in the back of your book, on page A4 and A5. So let me kind of explain what this is. So up here at the top, where it has these numbers, and I will give you these numbers on the test, you just have to know what to do with them. So, it has a neutron, and then it has an atomic mass of 1 point, and I'll explain the significance of this in just a second. 8.665 AUs, and then you have a proton, which is 1.0078. Okay? Those are numbers that you're going to become very, very familiar with. So, up to this point in your esteemed study of science, we've just said, hey, a proton and a neutron both have a relative atomic mass of 1. Because for what we've done up to this point, we can just call it 1. This is why carbon has a relative atomic mass of, Charles,
Oh, me?
12. And it's 12.0. It has 6 protons, it has 6 neutrons. Each one has a relative atomic mass of 1. And that's why it's 12.0. However, when you do calculations involving change of mass, you have to use these very, 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 very precise numbers. And again, if you look at this, you're talking a difference in the mass of these particles of 1, 2, 3, 4 tenths, hundreds, thousands, 10,000s of an atomic mass unit. Now, an atomic mass unit is really, 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 really small. So, one atomic mass unit is equivalent to 1.66 times 10 to the negative 27th kilograms, okay? That's a really, 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 really small number. So, this is the beauty of what science was able to do, is that, okay, number one, we were able to isolate the proton and the neutron, which is its own challenge, especially the neutron. And then we were able to find the mass of it, and not only we were able to find the mass and call it 1, we were able to find the difference in those masses to tenths, hundreds, thousands, 10,000s, hundreds, thousands place values. So in your normal day-to-day life, you can just basically call them 1. Where this becomes important is when you begin to do what we're going to talk about next, which is called binding energy calculations. So there's a couple of things that are on this chart.
Wait,
So what?
what do you mean next week?
Do we have a test in this class?
Yes.
On Monday?
On Monday. We said we'll talk about it next week.
Okay, well, I meant like, I missed
Tomorrow?
something.
You're confusing me.
No.
And scaring me.
I probably said when you look at this table, not next week, when you look at this chart. So, what you have, the column that you're going to need most is this atomic mass value. And these are all very, 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 very precise values. It also shows you the relative abundance. We'll talk about the decay mode later, beta minus, beta plus, alpha, that type of thing. And then this is the half-life, okay? How long do those exist? If you start with a certain percentage of it, how long does it take to drop to 50%? Some of these are extremely long, like beryllium 10 has a half-life of 1.5 times 10 to the 6th years, okay? That's a long half-life, all right? But some of them are very short, like one has carbon 10 has a half-life of 0.020 seconds, okay? Which means that if you have it, it's not going to be around very long. So, what I'm going to do is work one involving iron because this is like the classic example. So, we need to tie together a couple of ideas. One is Einstein's equation that E equals mc squared, okay? So, if you look at the units, Einstein can only have mass times c squared to get energy. Because if he said, hey, I think E equals mc, right away, why would everybody think he's an idiot?
Units are wrong.
Yeah, what do you get when you multiply mass by velocity?
Acceleration.
Momentum.
Momentum.
That's gotta be your ass stopped up, Bird. I wasn't even here for that part.
Mass
I
by
almost said-
velocity, you get acceleration.
I'm academic.
Who said that? Oh, you said accelerate.
Okay, how about momentum?
You could say
I could.
equals MV. I'll allow it.
Now, because the mass, oddly enough, needs to be in kilograms. And then you got meters per second, that's gonna get squared, which is 2 kilograms meters squared over second squared, which is the same thing as kinetic energy, which is 1/2 mv squared. Oh, that's kilograms meters squared over second squared. So the beauty of what Einstein actually figured out was that there's nothing in front of it. There's no 1/2, there's no 1/4, there's no fraction, there's no multiplier, it's just mc squared. So let me explain what this is. What this mass represents, and this was why a lot of physicists had struggled with this concept, was that number one, and this all came together at about the same time. They were trying to figure out how the sun worked, okay? Was it, for a while they thought, well, maybe it's literally a big burning chunk of coal or wood. And it's like, well, that won't work, it would have burned out, and it's not producing enough energy. And it was just weird anyway to think that our universe has a big chunk of burning coal in the middle of it. It's like, that's just weird. But they didn't have any way to explain, number one, how it was producing electromagnetic radiation, because keep in mind, this is about the time of Maxwell's equations, where they knew light had both an electro and magnetic field to it. It's like, okay, we're producing light, it's producing electric and magnetic fields, we're seeing light, we're getting this energy from it, there's no ether, how does that work? And then they developed at about the same time the ability to separate the light into its spectrum, and they saw this spectrum that they had never seen before, and that was the element helium. They said, okay, well, where's that coming from? Never seen that one before, and why is it showing up in the sun? So this all started to come together at about the same time. And then they also thought, well, Einstein comes along and says, hey, E equals mc squared. So the M part of this is, and this is a very, very short explanation. The short version is that you take, if you want to make helium, you take some hydrogen and you smash it together under extremely high pressure and extremely high temperatures, and then you make a helium atom. And if you were to compare the mass of the 4 hydrogen atoms to the 1 helium atom, the helium atom would have slightly less mass than the 4 hydrogen atoms do. And that difference in mass, and this is important, it's the difference in mass, not the mass, it's the difference in mass that gets plugged into the M part of this equation. And then you're multiplying that by the speed of light squared, okay? Well, here's the problem. To really work in kilograms, you're dealing with extremely, 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 extremely small numbers. So it has its advantages to work in atomic mass units, because it's easier to work in atomic mass units than it is to work in kilograms, because you're dealing with such really, 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 really small numbers. But to make the units work out, you can't keep C as velocity, because that's meters per second. So they did kind of a handy-dandy workaround. So if you, and I'll show you how the math works in just a second. So there's a conversion, it's on your purple sheet. I don't like the number that they have, there's a more precise value of it. So you have 93.14 mega electron volts, and sometimes you see this as per atomic mass unit, and that's the more pure form of it in terms of how the units work out. Or you can see it, oh, I wrote that down, that's 9.49. Why did I get 0.13? Hold on. Give me a second. Okay? Your equation sheet just lists this value as 931. Every other textbook in the world uses it as 931.49 because that's more precise. So if you look on that purple sheet, they've got it just as 931. When I work all mine, I use 931.49 because that's the more accepted value. So the units that you get out of this for energies are MeVs, okay, mega electron volts. So because you're multiplying by 931.49, it doesn't take much to get a lot of energy out of this thing. So if you're a purist, you can find the mass in kilograms and multiply it by the speed of light squared, okay? It's like, oh, Bergkamp, it's Einstein, I'm such a fan. You can do that. It's a god-awful amount of work, but it's just easier if you just use this number. So let me show you how this works. Typically what you're trying to find is what's called binding energy. So the binding energy is a comparison of basically, like we're going to deal with iron 56, I think, if I remember right. Yeah, iron 56. So what we're going to do is we're going to compare the mass of a single iron nucleus to the sum total of all of the protons and neutrons, okay? So we're going to make a comparison. So in other words, like if you were, I said, here's your lab final, kids. I want you to build, it's very simple, I just want you to build a nucleus of iron, okay? That's all you have to do. I'll give you all the protons, I'll give you all the neutrons, it's like a kit, okay? Here's your box of protons, here's your box of neutrons.